everyone, this is group 29 and we will be presenting on root locus analysis in control system. So one of the key concepts in control systems is to determine whether a system is stable or unstable, and the root locus analysis helps us to understand this clearly. So when we say root locus, what does it mean? It is a graphical method used to show how the root of a characteristic equation move in the S-plane as the gain increases from 0 to infinity. And why is this important? It helps us to determine system stability. It helps us to predict transient response characteristics. And these roots determine system behavior. That's if they lie at the left half side of the plane, it means the system is stable. And if they move to the right side, it means the system is unstable. So instead of solving complex equations repeatedly, root locus provides a visual approach to analyze system behavior. In this presentation, we will explain the concept and apply it to a third order system.
Good day, everyone. I'm Ohimi Richmond. So, to understand root locus to the core, we will try and learn about certain key concepts such as poles, zeros, branches, and stability. So, poles are the root of the denominator, which affects the system's behavior. Zeros are the root of the numerator, which affects the response of the system. Each pole creates a branch. So, for example, if you have 3 poles in the system, it means we have 3 branches. Using the S-plane, we can see that the horizontal axis represents the real part and the vertical axis represents the imaginary part. Also, to talk about stability, a system is stable when all the roots lie in the left half of the S-plane. So even if one root is found on the right side or the right half of the S-plane, the system becomes unstable. Also, as the gain increases, we find out that the roots or the poles move along certain path, which can be described as the root locus.
Okay, I'm Jackson. Our objective in this analysis are first to analyze system stability and determine the range of gain. Second, to identify important features such as real axis segments, asymptotes, and centroid breakaway points. Third, to determine performance parameters like frequency of oscillation, gain for a given damping ratio. Finally, to visualize how poles move as gain increases. All these help us design a stable and efficient control system.
Hello, good day. My name is Mujahid Abdullah, a member of Group 29. And my part is to start the analysis of the system. Here, the system is a third order control system, which means the system has 3 poles. When we look at the given closed loop transfer function, we are going to form the characteristic equation, which determines the system's behavior. So from this equation, we are going to identify the poles at 0, -2, and -4. Then, since there are 3 poles and no zeros, we are going to expect 3 branches of the root locus. So at this stage, we are going to begin constructing the root locus by applying standard rules. We first determine where the root locus exists. That's on the real axis first, by checking intervals based on the number of poles to the right. Then we also prepare to calculate some important features, such as the centroid of asymptotes, the angles of asymptotes, and then the breakaway point. So this stage will set the foundation for the full root locus analysis.
So if you encounter, I'm going to be continuing from the setup. So now we can determine the root locus features. which exists on the -2 to 0 and then -4 to infinity. And since we have the 3 poles and we have the 3 branches, so as the gain becomes very large, the branches move towards infinity along the asymptotes, and it intersects at the point called the centroid, which is the -2. And it also shows the direction of the pole movement for large values of gain and helps in sketching the Root Locus accurately.
That we can have a continue from where my fellow group member ended. To find the breakaway point, you solve 3s squared plus 12s plus 8 is equal to 0. This gives the breakaway point, which is approximately -0.85. Next, using the Routh-Hurwitz criterion, we determine system stability. The system is stable for 0 is less than k is less than 48. This is marginally stable at k is equal to 48. And it becomes unstable for k is greater than 48. The system begins to oscillate, marking the boundary of stability. This helps us to choose the correct gain for safe operation. Thank you.
So from our calculations, damping ratio being 0.5, the angle from negative roll axis theta becomes cos inverse of the damping ratio, which becomes cos inverse of 0.5, giving us an angle of 60 degrees. And from our root locus graph, the magnitude conditions are that OD is equal to 1.3, BD is equal to 1.8, AD is equal to 3.6. So when we calculate for K, multiplying everything we have here, all the magnitude, we get 8.424. Then our resulting value for K, when the damping ratio is 0.5, becomes 8.424. So now after everything, our results are that our breakaway point S is equal to -0.85. Our imaginary axis crossing K is equal to 48. Our frequency of oscillation is equal to 2.8 rad per second. And our constant K, when our damping ratio was 0.5, is approximately to 8.424.
So hello, please, I'm Theophilus Champon from Group 79. And from what my colleagues have said, when I take a final look at the Root Locus diagram, which we have here. So this horizontal axis we have here represents the real axis, and the imaginary axis here represents this vertical axis. This represents the imaginary axis, and we have crosses here. So we have cross at 0, -2, and -4. This represents the poles. And since there are 3 poles, that means you would have 3 branches, right? And now from the diagram, we would observe that the root locus just exists between -0 and -2. So -2 and 0, yeah, the root locus comes here. And from -4 to infinity. So that's kind of stable part, -4 to infinity. And we also notice that at approximately -0.85, which is somewhere around here. So when we trace it, we get this. The branches meet at the breakaway point, which is also called the breakaway point. That's it. And as gain increases further, the branches meet at the asymptotes and gradually meet at the centroid at -2. Yes. From the diagram, we can clearly see that the system transitions from a state of stability to unstable very quick. So from here, we see that it's stable, and all of a sudden, it moves to unstable here. So to conclude, whatever we've done here, the stable range is 0 to 48, and the breakaway point is -0.85, and the centroid is -2. The Root Locus is a very powerful tool for analyzing and designing control of systems visually. Thank you.